Hi everyone. In this video I'll give some directions to the students as to performance of the coursework. The subject of the coursework is simulation of processes in aeronautical engineering. The purpose of this coursework is to study and start using the industry standard software packages to simulate generic processes in avionics. I'm posting this Word document online on Moodle system of Kharkiv Civil Aviation Institute of Kharkiv National Ivan Kozyedub University of Air Forces. So all the students assigned for the course will be able to see this document and use it to prepare their reports. So let's take a look at this assignment. How to perform the explanatory note for the coursework. You'll have this title page. I don't have to explain it because it's pretty obvious, self-explanatory. The coursework contains two assignments, two tasks. First one is to use the MATLAB to simulate the linear dynamic links appearing in avionics, or actually in aircraft. The second will be the use of multi-sim software package to simulate some processes in avionic circuits, in avionics circuits. As the assignment for the first part of the coursework, we use as the linear dynamic link, we use the automatic control loop for the elevator of an airplane. How does this elevator looks like, and what is the elevator? I'm referencing you to this handbook. You can find something similar online when you Google just an elevator. There are lots of pictures online. So the elevator is the part of airfoil which is used to control the pitch of aircraft. The deflection of this elevator leads to changes in the angle of attack of the airfoil. But this elevator airfoil is part of the larger system, which is the aircraft body itself, including wings, which create a major lift for the aircraft. So these are used just for the attitude control and pitching moment attitude control. So we use the formal approach. The formal model for the aircraft pitching moment has the following form. We have two differential equations. The first differential equation includes the angle of attack. This first term of this equation is the derivative of the angle of attack over time. The derivative equals two formal terms. The first term is the angle of attack itself times the coefficient which describes the inertial properties of the aircraft, and omega stands for the rate of rotation of the aircraft around its center of mass by the pitching direction. So basically the derivative of angle of attack is actually the same thing as the rate of rotational movement of aircraft around its center of mass. But there is slight differences to these two terms. This one, the derivative of the angle of attack, is the simultaneous change of angle of attack. And this one, the omega, stands for the steady state one. So this differential equation describes the movement both in transient mode and the steady state mode when the derivative fades out and the transient mode is over. The second equation again includes the angle of attack times some coefficient which describes the influence of the inertial of the aircraft onto the angle of attack, some stabilizing properties of the aircraft, the next coefficient, and times the rate omega, the rotational rate of rotational movement of the aircraft around its center of mass, which describes the stabilizing properties of the aircraft body, which makes the aircraft not making this constant rotation but actually stabilizing at some angle of attack. And the delta here, the third term, delta here stands for the deflection angle of the elevator. Deflection angle of elevator times some coefficient which shows the efficiency of the elevator on the particular airfoil. So delta stands for this deflection angle, deflection. So suppose, and basically that elevation angle just was 0, and then at some point in time it gets deflected. So this deflection, this delta, can be simulated as the unit step function. But we'll get to this later as we proceed to the simulation in MATLAB. So alpha is the angle of attack, simultaneous angle of attack of the aircraft. Omega z is the rate of rotational movement around axis OZ, which is the pitching movement. Delta v, or should be v, is the deflection angle of the elevator. So the coefficients needed to simulate this system, which is kind of simplification. The coefficients are presented in the table. So for every variant you pick, there is a set of coefficients. There are 4 of them. 1, 2, 3, 4. All 4 coefficients are listed in the table. There are different sets of these 4 coefficients. So to complete the report on this coursework, you need to simulate formally this system represented by 2 differential equations in MATLAB. So I'm already having this MATLAB running on my computer, and how to run the MATLAB I tried to explain to you before. So we create a new model. We open the Simulink, and we create a new model. Now we take a look at the we open the Simulink library, and we take a look at the system. I'll put it here. So when I switch back to the Simulink library, I'll see the equations. So what do we basically need? We need, since we have differential derivative here, so to get angle of attack, we'll need to integrate this whole equation. So we need some integrators. Integrator can be found under the continuous section of the Simulink links, our standard tools. We drag and drop this integrator, first integrator here, and the second integrator here, because we have 2 equations and we need to integrate both of them. So 2 integrators. at the output of the first integrator, we suppose that we'll have alpha as the output, this alpha angle of attack as the output of the first equation. Then we need to take this alpha and multiply it by this coefficient and feed it back to the system plus some other value. So we feed it back to get this new derivative. So we need some gain here. The gain is the multiplier. Again, mathematical operations. We find this gain operator here. We put these gains here. Actually, for the second equation, we'll need 3 of the gain units. So I'll drag and drop 3 of them. 2, 3. I spread them. So supposedly we'll denote them or title them as according to our equations, but first we need to give some feedback. So we take the output, from this integrator and feed it back to the gain. Now after this gain we need some summation, because this first term in this equation is produced by this gain element, but we need to add it to the omega formally speaking. So we need to have the adder, the summer, the add unit. We drag and drop here, and the second one, the number of inputs for this adder is, for the first adder is 2. The number of inputs for the second adder should be 3. So we double click on this adder and increase the number of inputs by adding a plus sign here. So we have this adder unit containing 3 inputs. Now this omega, the second equation. So this gain should be connected to one of the inputs. So here we have the first term of the derivative at the left hand part of the equation. Now we form the right hand part of the equation. So this alpha, this A times alpha, will be represented at the output of this gain element. So it goes to adder. The second part, we need to have omega. Omega is the output from the second integrator. So we just connect this second integrator to the adder. And then we use this omega for the second equation when we form or generate the right hand part of the second equation. So we need to feed it back also, and we right click on this connection, on this link, to make a connection here. Oops, sorry. We double click, right click here and make a connection. This gain comes to the second input of the first adder. Sorry, this is wrong. omega comes here, omega from the output of the second integrator comes to the input of the first adder. And now we can feed this adder, the output from this adder, to the integrator. So here we have the derivative, the left hand part of the first equation, and then it goes to integrator again and it feeds back to the input, so the first equation will start working. Now we create the second equation, or simulate the second equation. You can make it look nice. So this error alpha from the output of the second integrator also will have to be fed here. We feed it here. We feed it here. So alpha, which is the angle of attack, is also has a feedback to the second integrator, to the second integrator through this second gain module. So alpha, the angle of attack, needs to be multiplied by this LA alpha mz. So we'll put these coefficients accordingly. This is omega is fed back to this first gain unit. We need to multiply omega by this coefficient, alpha mz omega z. And so we can connect these inputs of these two gain modules here. And the third element, the third term of the equation, is deflection. As the source for this deflection of the elevator, we use the so-called step function. The step function can be found on the sinks and sources. We use the step function. Or we can use the generator of the rectangular pulse generator, rectangular pulse generator. So we connect the input from the pulse generator, the output of pulse generator, to the gain input. And we connect this, and now we feed omega to the integrator, and then from the output of the integrator we feed it back both to the first equation through this error and to the second equation through this gain. So now let's set the parameters for the pulse generator. Let's say it have the period of 20 seconds. The amplitude will be 1 degree, and 50% of the pulse will be the pulse width will be 50% of the period. Okay. Now we set the simulation time for 20 seconds. We need to put these gains here. For example, let's take the first row, the first variant, as an example. So as the coefficient alpha y alpha, we need to set this minus 0.593. So we double click here and set the coefficient to minus 0.593, and we click on OK. Now the second coefficient, a mz alpha, which we multiply the angle of attack alpha with. So second, a alpha mz is minus 228. We multiply alpha. Alpha comes here. So this is the second, minus 2.28. Again, we're doing this formally, without discussing the physical sense or physical meaning of these coefficients. So we just do formally, we do formally create the system. So we set this one. The second one, the third coefficient, minus 0.529. We multiply this coefficient by the omega. Omega comes from this integrator, omega, so it should be here, and it enters the second equation. It's minus 0.529, and we click on OK. The third gain, or the fourth gain here, we multiply the deflection angle of the elevator by this fourth coefficient. So it's minus 12. We set it here, minus 12. So basically the system is ready to be simulated, but we need to put some additional elements to see what's going on. So we switch to the sinks, and we drag and drop the floating scope, or two floating scopes, to our system, and we feed the no, sorry, not floating scope, just regular scope with an input. Regular scope here and regular scope here. Now we right click and connect the output left click and connect the output of the first integrator. Sorry. Again, right click here. So I'm starting from this end. Okay, left click and we do this from the other end. Okay, we can make it look nice later. So the system is basically ready to be simulated. We click on this triangle here. The system is simulated. Then we double click on the scope and we see the output. We can auto scale the output, and we double click on the second one. Again, we auto scale the result. Now we denote or put a title to the first scope, angle of attack. Angle of attack. The second scope is the rate of pitching movement. So the first scope represents the angle of attack. Let's take a look at the oscillograms. What's going on with the angle of attack? So, and let's take a look at the input, the deflection. We can put the third scope here, and we connect the third scope to the input signal. Input signal is the deflection of the elevator. Again, we simulate, and there is the input. So we can see that, again, we outer scale, we can see this step or 2 steps. It's 20 seconds, but if we increase the simulation time for 40 seconds, for example, we get 2 deflections. Well, we have 2 periods of this same function. The deflection at 0 time, the elevator deflects by 1 degree, and then it stays in that deflected condition or deflected state for 10 seconds, and then comes back to the neutral position. The deflection angle goes back to 0, and then the process repeats itself. Now, let's take a look at these 2 outputs. Let's outer scale. Let's outer scale. So we can see that what happens to the angle of attack? As the elevator deflects, the angle of attack starts rising, which is obvious, right? From this picture, we can see that as the elevator deflects, something is happening to the angle of attack. The angle of attack starts decreasing. We can see this angle of attack oscillogram. And then what happens? The angle of attack reaches its maximum value, but then it starts increasing again. And there is this oscillating movement until the angle of attack reaches some stable value. So basically the aircraft wing as a system, as controlled by this elevator, behaves like a pendulum. It starts oscillating, and then angle of attack stabilizes at some stable or steady state value. When the deflector comes back or elevator comes back, the angle of attack starts increasing back from negative values. And again, there is slight oscillating movement of the angle of attack, and angle of attack comes back to normal, comes back to 0. So what happens to the rate of the pitching movement? And what is the pitching movement? The pitching moment is actually the aircraft starts rotating around the axis OZ, starts diving. The aircraft starts diving. And this rate of pitching, the rate of this diving movement, actually aircraft starts rotating in this pitching moment across this axis OZ. And again, there's oscillating movement. So the rate of pitch movement, the rate of rotation increases and then decreases, and then there's this oscillating movement, and the rate of the pitching moment stabilizes at some certain steady state value. So again, the whole aircraft behaves as a big pendulum. So the elevator moment tries to deflect the aircraft, change the attitude of the aircraft in the pitch. But the whole aircraft body is designed so that some stabilizing forces appear and start acting on the aircraft body. So this pitching moment doesn't get uncontrolled, doesn't get from under control. So we can talk about these oscillograms more, but this is basically it. We created a formal representation of the system in the MATLAB, and we obtained some oscillograms at the output. So again, I'll show you the system. The system is here. You can save it under your name. I'm saving this one under my name. Okay. And I close this one. So this is it for the first part of the video, and in the second part of the video I'll explain how to perform the second part of this coursework using the multi-sim package, using the multi-sim software package. This is the one. So until next time, bye.